Swayam Prabha. Digital India. Educated India.
We will now continue our discussion on simulation on water. So far from the PDB file for water, we have come up to the configuration.gro file. So let us continue with that conf.gro file. We talked that this file will have the coordinates of all the water molecules. We have 899 molecules and 3 times 899 is 2697. All the coordinates are written from third line up to line number 2699. Would that be the last line? Or?
Yeah, that would be the last line, and in the last line there will be the box length also.
Okay. What is the format on that last line?
The last line, the format is in nanometer 3.0 space 3.0 space 3.0. This is the format of the last line.
And so on the last line there will not be this 6 sol, 6
No,
or
no,
nothing.
no, no,
It will
no,
be
no.
just
It
X,
will
Y,
be
Z for the or not X, Y, Z, the box size.
Yeah,
X,
the
Y,
box
Z
size.
dimensions.
Yeah.
Okay. So what is the next step now from the GRO file?
So the next step is we have to have a topology file for water,
Okay.
because it will contain all the force field parameters, sigma, epsilon, charge and mass.
Okay.
So this is the topol.top file for water.
Okay.
So here the same thing, NB function, as I have already said earlier, if it is 1, it corresponds to non-bonded function and it corresponds to a 12-6 1 potential. So it can be changed according to the user, whatever they want to, potential they want to use.
Now these topol.top files, are they available on websites or we have to create?
Yeah, they are available on website, and you can create it as well from, if you have your PDB file
Okay.
of any molecule that you want to create a topology file of.
Okay.
Suppose you want to create a topology file of water. So you
Okay.
have the coordinates, you have the OH bond length and bond angle.
Okay.
So you have to enter the bond length and bond angle in amino acids.rtp file.
Okay.
This is a file which is contained in OPLS folder.
Okay.
And this is a folder in top folder. So top will be automatically downloaded when you install Gromacs.
Okay.
So it will have all the force field directive, charm, amber, OPLS,
Okay.
Gromos force field. So
Okay.
whatever force field you want to use, say OPLS or amber, suppose you want to use OPLS for water, so you have to go to the directory OPLS.
Okay.
There is a folder, a file, amino acids.rtp.
Okay.
You open the file using the command vi, go to the last line, just write the residue name of water
Okay.
and bond length and bond angle. Then you have to use the command pdb to gmx,
Okay.
and then input will be your pdb file and output be your topology file.
Okay. So maybe when we install Gromacs, show them installation, we will show how to create a top file.
Yeah. We can show them
Not
for
only
sure.
from the data that is already there, but also we can create our own.
Yeah, we can create for ethanol or methanol
Okay.
or some complicated
Right.
molecule as
Okay.
well.
Okay. So the first line is common parameter, or that is just a comment here.
The first line is a comment here that
Yeah.
parameter are taken from OPLS force
Right.
field.
So it is the fourth line, 1, 2, 3, fifth line really is the actual data.
Yeah.
The first default is part of every file.
Yeah, default is part of every file.
Okay.
So non-bounded function
Right.
depends on the user, which potential they want to use.
Okay.
Then there is combination rule 2. So
Now,
combination,
that combination rule 2 is not coming exactly below that comma.
yeah, that doesn't matter
So
actually.
it can be anywhere in that
It
line.
can be anywhere in that line.
Okay.
Then there is gen pairs.
Okay.
Yes, that will generate interaction between 1,4 interaction will be generated
Okay.
if you give yes. And
So what is the meaning of this 1,4?
1,4 is long range interaction between water molecule. So since in case of argon you don't require it, but water,
Okay.
since it is a triatomic molecule, so you may as well give yes to generate the interaction, long range interaction.
No, but in case of water you had 3 atoms.
Yeah.
Right? Now naturally anything 1, 2, 1, 3 is part of a given water
Part
molecule.
of a given molecule.
So 1,4 is outside the first molecule.
Outside the first molecule.
But suppose instead of water we have a methane. So
Yeah.
methane will have 5 atoms.
5 atoms.
So do you call the interaction between 2 methane as 1,6?
2 methane, 1, 2, but it is not, it depends on which atoms you are counting on, right?
Okay. But see, just as for water I have OHH.
Yeah.
So in methane I will have CH1, H2, H3,
H3,
H4.
H4, yeah.
Right? So 5 atoms are for methane. So if I want between one methane and another methane,
Yeah.
you may call it 1,4 as a nomenclature.
Yeah.
But in
In
reality
reality,
it
it
is
will be
1,6.
1,6. Yes.
Okay. So when you say yes for gen pair, that means
It
is
will generate-
intermolecular,
Yeah.
not intramolecular.
No, and intermolecular will be when there are more than 4 atoms, say in case of ethanol.
Okay.
There will be 1,4 interaction in case of ethanol.
If it is a rigid molecule, there really shouldn't be.
Yeah, but in reality, it is not a rigid molecule. The molecules are allowed to move.
So
You just you can fix the bond length and bond angle, but the
Okay.
molecules move in the simulation box. They are not fixed in some
So
place.
it means 1, 2, 3, you don't want this to change, but 1, 4,
Yeah.
you are allowing it to interact.
Yeah, and this fudge LJ and fudge QQ, these are the parameters to model this interaction. Fudge LJ is the Lennard-Jones parameter, and fudge QQ is the electrostatic interaction parameter. So this will model the 1,4 interaction.
Okay. So that fudge LJ, fudge QQ is always for intermolecular.
Yeah.
Okay. But why that fudge LJ is 0.5 and the other one
The
0.83?
maximum value is for fudge LJ and fudge QQ is 1.
Okay.
So the maximum you can take 1, not more than 1.
Have you tried other than 0.5 or 0.83?
I have tried 0.6 for fudge LJ and for fudge QQ 1, and I have tried 1 for both, but it doesn't really change the interaction or the
The
results.
overall results?
The overall results are more or less affected by the sigma epsilon values and charge values rather than this fudge LJ and QQ values.
Okay. So that is the first line which tells about the interaction.
Yeah.
Then one blank line and atom types.
Yeah, atom types you have to describe the charge, mass, and you have to give the value of sigma and epsilon.
Okay.
So since there are 3 sites, oxygen and hydrogen, and both the hydrogens are similar,
Correct.
so both will have same mass. Charge for oxygen is minus 0.8476 and for hydrogen it's 0.4238. Then sigma and epsilon for hydrogen is 0. And for oxygen, the value is 3.1 into 10 raised to the power minus 1 in nanometer, and epsilon is in kilojoules per mole.
Okay. And now you should all notice that the charge on oxygen is minus 0.8476. So for each hydrogen, it is half of that.
Yes.
Because the sum of 2 hydrogen charges should be equal
to the sum
oxygen charge, so that the molecule is neutral overall.
Yes.
Okay.
So
And that. What is that next line then? Include water.itp?
Include water.itp. In water.itp we will have the bond length, since in case of water there are 2 bonds.
Okay.
So we'll have to provide the bond length, bond force constant, bond angle, the bond angle force constant, and if there is any exclusion, like any interaction you want to exclude from your simulation, all these are to be provided in the water.itp
But
file.
ITP file we had already created, or we have to create now?
ITP file you have to create now.
It is not yet created?
No.
Okay.
And then there is system you have to define, whatever system you want to simulate.
Okay.
And then there is molecule name and number. Molecule name you have to give the residue name.
Okay.
And you have to change the residue name accordingly in the topology file, whichever molecule or atom you want to simulate. And number is 899, it is a total number of molecule which is taken in the simulation box.
It is the same as before, we cannot change that.
Like you have to change it according to the number of molecules you are taking.
Okay.
Whatever you are giving as an input in INP file, say if it is 900, you have to give 900 here.
Okay.
Else it will show an error. So now we will come to water.itp file. So this is the ITP file format. Right. NR, so first you have to define the residue name of water. So that is SOL sol. NR in atoms, it is the atom number, since there are 3 atoms, so it's 1, 2 and 3. Then there is type, which defines the atom type.
No, before that you have name is sol,
Yeah,
and NR.
that is the excluded interaction.
Okay, what is the meaning of that?
It is the number of interactions you want to exclude after certain atoms, like after 3 atoms you don't want to count the interaction.
So if it is methanol, I will be, sorry, if it is methane, will I be giving it as 5?
Yeah,
Huh?
yeah. It
So-
will change from molecule to molecule.
So it depends on the total number of sites on a molecule.
Yeah, and which kind of like if you are taking united atom or
Okay,
if
then the
you are
sites
taking,
will be different.
yeah,
Now, what will happen if there is a mixture instead of a single molecule? There will be two ITP files or only one?
there will be two ITP files for two. Suppose there is water methanol mixture, you will have to have a ITP file for water and a separate ITP file for methanol.
So, in this case, both will be solvents, but N or EXL will be different for the two.
Yeah,
Okay, so that is then you have this.
type
Okay.
which is atom type. Since there are three atoms, OW, HW and HW, then there will be residue number.
Okay.
Okay, and then there will be residue name, so which is SOL solvent. Then there is atom name. There is OW, HW1 and HW2. Then there is CGNR, that is charge group number, and then there is charge you have to define, and then there is mass. Mass on each atom has to be written there, and then there is a function DOH and DHH. So this is the OH bond length in nanometer, and then that is the OH bond force constant, and these are the exclusion.
No, DHH is a force constant or the distance between hydrogens?
Oh, sorry, DHH is the distance between hydrogens.
So they can actually calculate it from the coordinates.
Yeah, they can
Coordinate file.
calculate,
Okay.
and DOH is the bond angle.
So that force
Bond
constant
length.
you will mention it somewhere else.
Yeah, I'll mention it.
Right.
Actually, it has to be mentioned in the ITP file itself.
Okay.
So I think I have to change the ITP file a little bit. I just
Okay.
have to add one extra column in that after DHH itself.
So to give the force constant.
Yeah,
Okay. So now what are the last lines now?
those are the exclusion. When you create an ITP file
Okay.
from a topology file, these exclusions are automatically created. If you don't give it as well, it doesn't matter.
So which means if I skip the last three lines, it is okay.
It is okay, but you have to give the bond length, bond angle, that has to be provided there. So now we have ITP file, topology file, and we have GRO file, and MDP file is already there.
Okay.
So now we'll proceed through the energy minimization of water. So these are the three files that are required: conf.gro, topol.top, and em.mdp. MDP is for molecular dynamics parameter file, and EM is for energy minimization. So to perform energy minimization, first we have to generate a TPR file using the command grompp. So grompp space -f space em.mdp space -c conf.gro space -p topol.top space -o for output em.tpr, and then space -max12. So it will generate a TPR file em.tpr, which will contain information about the MDP file, GRO file and topol file, and it will be an input for the MD run.
MD run or minimization?
MD run for energy minimization.
Okay.
So next we'll do MD run. So MD run space -v space -deff_nm space em. So it will create all the output file which will have initial as em. So the output file will be em.gro, em.xtc, em.edr, em.log, like this. So whatever we have, will give the TPR file extension like em.tpr. In MD run we have to give the same name, em. We cannot change it.
So now the grompp, the output was em.tpr.
Yeah.
For MD run -v,
Yeah.
what is the input for MD run? em.tpr.
em.tpr.
Nothing else.
Nothing
because
else.
that em.tpr contains all information about MDP,
Yeah,
GRO, as
GRO
well as
and
top.
topo.
Okay, and def nm em means all files will have em as the initial part.
Yeah.
And how many outputs does MD run create? That you will have in the next slide.
There are many output, like you will have EDR file, you will have energy file,
Okay.
you will have XTC file which will contain the trajectory, then you will have GRO file definitely which will be the energy minimized configuration,
Okay.
then you will have log file. It depends on what files you want to have.
So
What are the
instead of MD run -v def nm,
Yeah.
I could have given all the files name relevant to that.
Yeah, all the files name relevant to that,
And
but it will
those
be
could
a
have different names now.
Yeah, but that will be a long command, and it's easier to have it, because then you will know that okay, em.gro is the energy minimized configuration, or if the file name is em.edr, which will mean that it is the energy file for energy minimization.
So the whatever you said now, if I say MD run minus H,
Yeah,
it will give me all the details.
Yeah, it will give you all
And
the details.
if I see the minus V option,
Yeah,
then I will know what it is going to do. It explains that?
yeah, it explains that.
Okay.
So after energy minimization is done, something like this will be displayed in the screen.
Okay.
So you see that the steepest descent algorithm that we have already discussed in liquid argon. So here also we use the same algorithm for energy minimization, and it is converged in in 22 steps, and the potential energy is negative in this case.
Okay, because you have lots of plus
charged,
minus interactions.
yeah, exactly.
Okay? And that less than 1000 means the maximum value of force is less than 1000
Kilojoule per mole per nanometer.
Not angstrom.
No,
Okay.
everything has to be in nanometer,
Okay.
distance, time has to be in picoseconds, energy has to be in kilojoules per mole.
So now potential energy will be again kilojoules per,
Per
mole.
mole, yeah.
And maximum force, it
Is-
is not giving the units here, it is
No.
understood,
Yeah.
right?
The maximum force is 7 into 10 raised to the power 2
Huh.
kilojoule per mole per nanometer on atom number 2497.
And so what is the norm of the force?
That is, I guess, the tangent of the force. I think so.
Okay. So where, suppose I want to know the meaning of norm of force.
You
The
can get
manual will tell
it,
me?
yeah, the manual will tell you
Okay.
what does it mean.
Okay.
So now we have the energy minimized configuration, which we will use for our full molecular dynamic simulation.
Okay. Now all these files are saved in the water directory,
Yeah, all these files are saved in water directory.
and that is already under Gromacs.
Yeah,
But why it is not showing that Gromacs there? Because
because I have done it in a different server, so
Okay.
it is not showing there.
but the water directory is in the Gromacs.
Yeah, water directory is in Gromacs. So when we perform simulations here,
Okay.
when we will show them on screen, it will show as Gromacs. If you give PWD, you will get the path.
So I will get the path here.
Yeah.
So what will the path be like approximately?
The path will be like home, then your name, then downloads, then Gromacs, then water.
Okay. But you have put all these things in downloads file only?
Yeah, but it depends on you. You can as well change
Okay.
it from downloads to, you can create a folder named Gromacs in your
Somewhere else,
desktop or
somewhere else.
documents or
Okay.
downloads or in your hard disk, and there you can
Okay, right.
install it as well.
So now we have finished the energy minimization.
Yeah.
Okay.
And now we will use the GRO file of energy minimization for full molecular dynamic
So what is that
simulation.
first line? Go back. That /emgro. What is the meaning of that?
Okay, actually if you already have a file em.gro, it will override the file to that.
Okay.
So
right,
that is
right.
the command.
Okay.
So for molecular dynamic simulation of water, we now have the energy minimized configuration em.gro,
Okay.
we have topol.top, and we have full.mdp file. So
Okay.
these are the files that are required. So we'll type the same command to generate full.tpr file. We'll use the grompp command, and grompp space -f full.mdp, which is the molecular dynamics parameter file for full molecular dynamic simulation of water. Then -c space em.gro. em.gro is the energy minimized configuration of water. Then space -p topol.top.
So that will remain the same whether it's minimization
Yeah,
or
yeah, yeah.
molecular dynamics.
Because it contains the information about water,
Right.
so it's not
What
going to
about
change.
full.mdp? That is different from
Yeah, that is
minimization?
different from energy minimization, because in full.mdp will have detail
More
about
information.
in which ensemble you want to simulate. Suppose you want to do it in a NPT ensemble, so you have to fix the pressure, temperature, you have to use algorithms for that. And then since in this case we are simulating water also, you need to constrain the bond length and bond angle as well.
Right.
So we will have those constraints
But
algorithm.
those constraints are the same for your minimization also.
In case of minimization, we don't actually use constraint.
But
In
unless
In case of minimization, we just have to give the algorithm name,
Okay.
which algorithm
so
you.
but minimization really doesn't change the bond lengths and bond
Yeah.
angles, because if it did that there will be a huge problem.
Yeah.
So minimization really calculates one energy, then you use steepest descent.
Yeah.
It will go along some slope and get the
Minimum.
lowest energy.
Yeah.
Okay. So now this is what is the end result of it? Full.tpr.
Full.tpr is the end result of this, and this TPR file we will use for MD run.
Okay.
Just as in case of energy minimization, we used em.tpr for
Okay.
our MD run.
Right.
So the command is same, MD run space -v space -deff_nm space full.
Okay.
So it will create all the output file which will have full as an initial.
Right. So now before we really go further, what will be the main output files after this?
The main output file will be full.gro and
Right.
full.xtc. XTC file is the main
Okay.
output file because this is the trajectory file and
Right.
this will be used in all the analysis.
Okay. And now, suppose at the end of the simulation,
Yeah.
I want the last configuration.
Yeah.
Where is that saved?
That is saved in full.gro.
So full.gro has just one last
One last,
configurations or many more?
it has one last configuration. So if you want to have the last configuration, suppose you have done perform simulation for 10 picosecond.
Okay.
So you want to have the configuration for the 10th picosecond, right?
Okay,
So what you will do is you convert your XTC file
Okay.
to full.xtc file to full.gro file.
Okay.
So just type the command, you have to use the command trjconf.
Okay.
So it will convert your trajectory file to a GRO file.
Okay.
So now your GRO file will have configuration for each time frame. Like if you have given 2 femtosecond as the time step,
Okay.
so at 0 time it will have the configuration, then after 2 femtosecond it will have configuration. So you have to convert your XTC file into a GRO file using the command trjconf, and then you will get the configuration for the last 10th picosecond. At each time frame will have configuration.
But suppose I want just the last configuration
So still you have to convert it using trjconf,
and then remove all the things except the last,
or you can just copy the last configuration in
Okay.
some other folder.
but there is no automatic way of doing it.
No, there is no automatic way of just getting one configuration, one time frame configuration. You have to convert the XTC file.
Okay.
Suppose you want to convert the, you can give the beginning time and end time, but it has to be between some time frame.
So suppose my beginning time and ending time is the ending time.
But then the simulation will not run. It won't. The
No, no,
command.
no, I
The
already-
command will say that your beginning time and end time is similar, so it cannot execute. So you, suppose you give the beginning time as 9.5 and end time as 10.
Yeah, no problem.
No problem. It will work. But your beginning time and end time has to be different.
But as long as there is one delta t between, that is okay.
Yeah, that is okay.
So I will be able to get two configuration, not
Yeah.
one.
Yeah.
Okay.
And you'll
didn't
have different
didn't
box
you
length.
restart your simulations from the last configuration?
Yeah, you can restart simulation from your last configuration. Suppose it is crashed, so you will have a CPT file,
Okay.
and you can restart it.
Okay.
I'll show it basic.
Yeah, when we install, we will see
Yeah,
that.
we'll-
Okay. Yeah.
So now since we have performed full molecular dynamic simulation and we have full.xtc file, so we'll proceed towards the analysis of the
Okay.
trajectory. So after the end of the simulation, something like this will be displayed. So 1.22, 1:22 is the time that is required to finish the simulation, since it's just 20 picoseconds. So it took 1 minute 22 seconds to finish the simulation.
On a big machine, on
Yeah.
a PC, how long will it take roughly?
Depend on the system actually.
Okay.
So now we'll analyze the trajectory. So first we'll see the since in case of water we have 3 sites, so we have to create an index file in this case, as we did in case of argon. So to create an index file, we have to type the command make_ndx, and then we have to use GRO file. We can use any GRO file like conf.gro or em.gro or full.gro. Any GRO file will work. And then space -o, which is the output file command, space index.ndx. And then when we type enter, something like this will be displayed, where there will be system, water and sol.
Okay.
So since we have 3 sites, so we have to create index file for each and every site.
Okay.
Right. So to create index file for say,
Now let us, whatever is on the right side,
Yeah.
comment more on that index file.
okay. So see, there is by default, if you just type the command make_ndx -c em.gro space -o index.ndx, and then if you type q, it will just save and exit the file, and by default there will be 3 index file created. One is the system, one will be water and one will be sol. So all these 3 files are same.
Okay.
But now since we have 3 different sites in water, we need to create index file for all these 3 sites, because we'll calculate radial distribution function, right? And we will calculate the site RDFs.
Correct.
So we need to have index file for different site as well. So to create
So whatever box you have shown on the right,
Yeah.
is that an index file?
that is not an index file, that is just a command you have given, and after that command this will be displayed on the screen.
Okay. That
Now
is
you
just
have
the display, screen
Yeah.
display.
So now if you want to just save and exit,
Okay.
You just type Q.
Okay.
Now if you want to create index file for different site, suppose you want to create for different atoms in
Suppose
water.
you want oxygen of water.
Yeah, so then you have to type A which means atom type,
Okay.
then space OW.
Oxygen of water.
Yeah.
So which means whatever is on the right side of the screen,
Yeah.
when you type the make_ndx, execute that,
Yeah.
that will appear. You have to type Q to come out of it.
Yeah.
Then type a.w.
No. If you just type Q, then it will come out of it.
Correct.
But then first you have to type, but then if you want to create index file for separate site,
Right.
you don't type Q initially. First you type atom type OW,
Okay.
A space OW, then something like this will be displayed. So found 899 atoms with name OW,
Okay.
right? Because
there are 899 oxygens.
yeah, and then
So, which means after you execute make_ndx, you have to do that a.w.
A space OW.
OW. Okay.
Okay. Then we have to, then there is hydrogen also. So you
Okay.
type A space HW1. A is
Okay.
for atom type,
Okay.
right? It will again display something like this.
Okay.
Found 899 atoms with atom name HW1. And since both the hydrogen atom are similar, so you don't need to create two separate index
Correct.
file for two hydrogen.
Now see, it says 3OW899. First box.
Because first is first atom is third one will be oxygen atom. So
Okay.
and then finally you type Q and then enter. It will save and exit the file.
So in the two boxes in the middle,
Yeah.
it says 3OW on the top and 4HW1 at the bottom.
Yeah.
So that 3 and 4, what are the meanings of that?
3 is the index file for one oxygen, then 4 is the for the fourth oxygen hydrogen, then 5 if you type AHW2 there will be 5HW2 because 3, 4, 5 this will be the sequence.
That is not clear. Can you clarify that a little better?
Okay, found 899 atoms with
Right.
atom name OW.
Okay.
So 3 OW, 3 is the like see 0 is the system, right?
Okay.
1 is water,
Huh.
2 is sol. Sol
Okay.
is the solvent.
Huh.
So third index will come as oxygen of water.
Okay.
This will come 3 OW then space 899 atoms. So
Okay.
after 0, 1, 2 you will have 3 as OW, then you will have 4 as HW1. Then if you want to create another index file for HW2 you will have 5 HW2. So when you analyze the trajectory file, suppose you want to calculate a radial distribution function, when you type the command G_RDF you will get a display of 5 like what do I say 5 separate residues. Okay. First 0 will be system, then 1 will be water, 2 will be solvent SOL, then 3 will be OW,
Okay.
4 will be HW1 like this.
Okay.
So when we go for RDF we'll see the index
Okay.
file what 3 and 4 actually means. So now we have index file. So now we'll calculate radial distribution function between oxygen site of water molecule. So to calculate we have to type the command G_RDF. RDF means radial distribution function, and there are 3 input file that is required for each and every analysis. First is the XTC file, second is the TPR file,
Okay.
and third is the index file. Right? Index file we have just created. TPR file we have an XTC file we have already in the folder, and then -O is the output file space OW_RDF.xvg is the file name of the RDF file. OW means we are creating
Oxygen of water, oxygen of
yeah.
But that could be any name, no? I don't
That
have
could
to
be
call it.
that could be any name. That depends on the user what he or she wants to
It
give.
could be just a.xvg.
Yeah, it
Okay.
could be that. So after you type the command you will have to select a group. So now you see there is 3 and 4 coming here.
Okay.
So that 3 OW899 was that in index file the third index is for oxygen of water and the fourth index is for hydrogen of water.
Okay.
So that is what 3 and 4 meant previously.
Okay.
Okay, so now since you have to calculate
But for 0, 1, 2,
yeah.
it is showing 2697.
Yeah, because there are total number of sites in the system. Like
Okay.
since there are 899 water molecules, so it will have 2697 site. So it is containing the overall system.
Okay.
And now we have created for different site for OW and for HW1. So it contains 899 and 899 water
Okay.
and HW1.
Okay.
So now to create a radial distribution function between oxygen of water, first we have to type 3 and then again we have to type 3 because we are creating GFR between
oxygen
and oxygen of water.
Okay.
And now to view the file, you have just to type xmgrace space the XVG file name.
Okay.
So it will automatically come up in the screen as it will be displayed in the screen. So this is the radial distribution function between oxygen site of water molecule.
So you have to type that 2 times.
3 or 4. So
Right.
suppose in 3,
There is
group 3 is the oxygen of water molecule.
So
So
when
you
you say
have,
select a group, you have to type 3.
and then again it will come select a group, you will have to again type 3.
3. So it will give oxygen.
Yeah, it will give oxygen. So this is the graph.
Right. Okay.
X axis is the distance between oxygen and y axis is the RDF.
Okay. Now if you want between oxygen and hydrogen,
So between oxygen and hydrogen we have to type the same command,
Okay.
give the output file name different so that we can distinguish it.
Okay.
And then when it asks to select a group, so first you need to select oxygen, that is group 3, and then you need to select group 4, that is hydrogen.
Okay.
And now to plot it, just type xmgrace space the XVG file name,
Okay.
right? So it will give the plot like this.
Oxygen
And hydrogen.
So for hydrogen it will be 4 and 4.
Yeah, for hydrogen, same command,
Yeah.
output file name has to be different and you have to type group 4 twice.
Okay.
So 4 has to be typed twice.
Yeah. So now since we have to conclude in 2-3 minutes, can you show the diffusion behavior also?
Yeah. So for diffusion, we have to use the command G_MSD. MSD is the mean square displacement.
And the other 3 are the same?
Other
and
3 are
last
the
one
same.
Is different.
Last one is different because last one this is MSD.XVG.
Right.
So when you type it, you will again be asked to select a group. So you type 2 or 0 or 1 because we don't want diffusion for a particular atom. We
Okay.
want diffusion for the whole molecule, right?
Okay.
So you just type 2 or 0 or 1. So it will display the diffusion coefficient value on screen, which is 2.3 into 10 raised to the power minus 5 centimeter square per second.
Okay.
Within bracket is the error bar. And if you want to view the file, you just type xmgrace space msd.xvg, something like this will be displayed, which passes through the origin.
So if they want to calculate the MSD, they can calculate the slope of this.
Yeah,
And they
or
should get the same value that was
value.
in the printer.
Yeah, exactly.
Okay. So we will conclude this lecture. It was a little hurried at the end. It is okay. We will actually demonstrate it using the Gromacs. So next time we will consider something about the mixtures. So we will conclude here and see you next time. Thank you.